Get ready to set up. Get ready to go.
Ready.
Hi everybody. Can you hear me? Great. Oh, we've got a good full house. I have the pleasure of introducing Hannah Vagasky. Sorry, I have to keep practicing. Hannah is a graduate of this department. She was an undergrad here in 2010 and is very excited at all the upgrades in the room in that amount of time. For those who've been here for a while, it's been really nice to see Hannah's been enjoying the upgrades to her building. But as an alumni here, she moved on to University of Washington for her PhD. During her time in Bob House's research group, she got a lot of field experience. So she went everywhere from the west coast of Washington State to the Indian Ocean, doing field campaigns, primarily focusing on observations and radar data. After her PhD in 2016, she moved on to Boulder, where she worked for NOAA, the GSL division, where she became a modeler and worked on developing convective parameterization. So Hannah brings experience from kind of both sides of the field, which she's now bringing to her current role, where 3 years ago she started at Atmospheric and Environmental Research, AER, which is a research arm of a private company that keeps changing names and who owns it. So I actually haven't kept track of who owns it. I was like JANUS or something. Anyway, she's the research arm of a private industry. She works there remotely. She's actually just down the road in Fort Atkinson, and she grew up in Wisconsin. Since she's been here, she's been part of another field campaign getting back into observations. The ICECHIP campaign was a major hail field campaign this year. She was out there 6 weeks, going everywhere from South Texas to North Dakota, chasing hailstorms. So she's here to share her perspectives from both that observational and modeling perspective on what we're learning about hail. And finally, as I always like to do, I like to share a little bit about, personally about our speakers. Hannah's a gardener, and that's kind of an underestimate. She just told me that they only have 100 gourds this year. So that gives a sense of the scale of which Hannah gardens. It's pretty remarkable. So she's the person to talk to about gardening. All right, with that, Hannah, take it away.
Great, thank you. Yes, I'm very happy to be here. It's been great visiting again. I'm going to be talking about hail melt, or hail, specifically hail melt. And I have several collaborators. I have them listed here. Some of them are from AER, but then we also have some from NCAR and NASA. So it's been really great working with a bunch of different groups. So to start with, just kind of basics. Why do we care about hail? Why should we study it? Why did we have this giant field campaign about it? And it's really an economic, agriculture, and safety hazard around the world. This is a graphic that was published by State Farm, showing how much hail damage they paid out last year. This is the top 10 states. Most of them are in the plains, but not all of them. All of them, they paid out at least $100 million in each of these states, with Texas taking the top at over $1 billion of payout from it. Our state climatology office says that last year, $2 million of claims of hail damage occurred in Wisconsin, and I like to kind of emphasize, or bring out the fact that 85% of that was due to crop damage, and that's one thing that's kind of unique, or we don't really think about. Usually when we're thinking of hail damage, we're thinking the big hail, that's what dents our cars and our houses and everything, but even small hail is really bad for farmers. So this is a headline from 2018, so it's a while ago, but it's out of France, and it says that they had an unprecedented storm. They had pea-sized hail, and it destroyed their vineyards. So even small hail is important. And then finally, I like to emphasize what State Farm doesn't bring up is that hail is still a safety concern. Even in the U.S. with our weather service and our radars, it's still a concern. This is a headline that came out of Colorado 2 or 3 years ago when there was a hailstorm that came off the mountains and went over Red Rocks Amphitheater. It was not warned, and nearly 90 people were injured, including 7 hospitalizations. And then also, safety is a concern for farmers with their livestock. That's something you hear from farmers, which is unfortunate. So there's a lot of parts of hail you can study. So why do I study melting hail. And there's kind of two ways that it's important from the impact standpoint. One is velocity, and one is being just how fast the hail falls. That's going to impact how much damage you can do. And then there's the size factor. Size factor is influenced, yes, by how big the hail can grow in the storm, but also melting can have a really big impact. This is a graphic that comes out of Merlot 2021, and so they're comparing storm observations, so that's what's shown on the left-hand side, storm reports, which are not perfect, but they're storm reports, and then the right-hand side is representing graphic as what we would expect for significant hail out of a radar, an algorithm. Again, the algorithm's not perfect, but it's what we have, and the top row is the spring, and the bottom row is summer, and you can see during spring, those two graphics compare pretty well, but in summer, you see the radar says there's a whole lot more hail than what is reported. And yes, there is issues with reports, but it does suggest that, especially in summer and especially in the southeast U.S., these storms produce a lot of hail, but it doesn't mean a lot of it's getting to the ground. So kind of need more understanding of like, okay, so what if we just have these algorithms based on radar, it's going to give us the wrong picture. So we need to understand this a little bit more. There's a couple ways we study hail melt and hail terminal velocity. The standard often is laboratory studies. Wind tunnels are common. That's what this figure is. It's a bunch of showing little pictures of a hail suspended on a string, and then they subject it to different conditions and take pictures of it doing like it's shedding drops here, and they'll weigh it repeatedly. So you can get it directly that way. There's also observations. There's been field campaigns. These two images are from two in the 1970s to 1990s, 2000s. ICECHIP, which I'll talk a little bit before, is the first one in 40 years in the US. But these are different ones. The picture in the center, they cut a hole out in a van and drove it out on the plains of Colorado with a mirror and a camera and let the hail fall in. So what you're seeing is the little hail falling in and bouncing off in this image. And then I'll also be using some data from this T-28 aircraft. This is something they will never do again. The South Dakota School of Mines bought and retrofitted an aircraft so that they could fly it into hail storms. So from the 1990s to the early 2000s, they flew this plane through hail-producing storms, which nowadays will never happen again. And then more recently, radars are becoming more of a thing. And then there's also theoretical modeling of how individual hailstorms work. And out of these, one of the most common is we get parameterizations. And so this is a flow chart from Morrison et al. 2020, which I like, kind of shows just how microphysics parameterizations are kind of developed, where you start on this left-hand side where you get knowledge from labs, observations, theory, and you create this microphysics scheme. And then at the same time, you take observations to help tune or refine it and things like that. So from the hail perspective, there's been a lot of studies that have developed this side of things since the 1960s. There's a handful of hail melt and hail terminal velocity parameterizations out there. However, there hasn't been a whole lot of work on integrating observations into that side. So that's kind of where we fit in. We want to use observations and models to look at hail melt and evaluate these parameterizations. From here, I'm going to give a little bit of like what do I mean by hail trajectory modeling. One of the simulations we did of a supercell that was actually flown through by the T-28. And then the second half is all about what we're doing now to further evaluate these parameterizations. I'll go through kind of three things we're doing. Each one's going to be a little bit more preliminary, so there'll be new ideas. But yeah, the first part was just published this month in the Monthly Weather Review. So we'll start with hail trajectory modeling. Hail trajectory modeling basically directly simulates the path a hailstone takes through a storm and the processes that are acting on it. So this figure here is how you often sometimes see a hail trajectory model visualized. So this is X, Y, and Z. And then the colors are the size of the hail, and the path is showing like where the path would go for the hailstone. So you can kind of imagine there'd be like a storm in here. But the hail starts small with here, and then it evolves, and then it's falling out over here. And there's a couple different methods or options you can use. Hailcast is one that's pretty common. It's available with WARF and then CM1 as well. What I've done is I've taken a portion of Hailcast and made it and so it can run in Python. So I'm just considering falling hail, so just this little part of the model. I only have parameterizations that represent melting and terminal velocity. I also include droplet shedding. But there's no hail growth, and if the hail is swept upward by the updraft, I stop tracking it. So it's just falling hail. I also initialize it with an assumed hail size. We do this a couple different ways, but we just assume a hail size to start with, and we assume right now that hail is spherical. The environmental conditions are also assumed based on a sounding. We do modify it, so we assume above the LCL, you're in a cloud, so we saturate it above the LCL. And then we also assume a vertical velocity. We right now have it constant in time and just a basic profile, but you can use observations of it if you wanted. And then the unique factor of our model is that we actually have implemented multiple melting and terminal velocity parameterizations, so you can actually directly see how these different parameterizations respond to the same environment. And so that allows us to directly compare them. So I'm going to be highlighting several parameterizations that we're working with. These are most of the ones you'll see. At the end, there'll be a couple additional ones, but these are the main ones. We mainly focus on 3 hail melt parameterizations. They are all use kind of the same idea, basic heat transfer equation from McLaughlin 1963, but they differ in some of their empirical assumptions. And so we have Rasmussen and Heimsfield 1987. This is the most common one you'll see out in the literature. There's also Wang and Chu 2020 and Zhang and Liss 1994. They all kind of differ a little bit on the assumptions they make, and then also what the characteristics of the hail. Some of them assume they're hail, some are smooth, some assume that they are lobed or non-spherical. Most of them don't assume there's no tumbling or anything like that. There's a little more differences in the terminal velocity parameterizations. I'm going to be highlighting 2 different types. The first one was also published in Rasmussen and Heimsfield 1987. This is based on 2 parameters known as the Best number and the Reynolds number. These basically describe kind of how the hail moves in a fluid, like the fluid dynamics theorem. They're just theoretical numbers. And then there's Heimsfield et al. 2018. This is actually empirically derived. So what they did is they had previously they 3D scanned hailstones and they printed those out, and then they put those in a wind tunnel, and then they got an empirical relationship between the maximum diameter of the hail and the terminal velocity. So that's those are 2 very different types of how we get terminal velocity. You'll see those results in pretty different results. So the storm I'm going to be looking at is actually from 2000. It occurred in Kansas. It was from the Steps Field campaign, and this is one of the flights that the T-28 went through. So the T-28 had a laser hail spectrometer on it that could measure hail up to about 50 millimeters, and they would fly above the 0 degree level. So you get estimates of the hail size before significant melting. This figure here is showing on this day when the T-28 was flying through, when it was sampling hail or detecting hail, the black lines is showing it. And in this case, in 2330, you can see the plane went through a 60 dBz core. So there's stories of like the pilot like ducking under the windshield. So it's not going to happen again. It's very unique. And we got this data from Andy Heimsfield and Aaron Banzimer and NCAR, and they're working on, since this is like 30, 40-year-old data, they're trying to go back and work with it some more, improve it. The other hail melt aspects we use, we assume the vertical velocity is just a constant 5 meters per second above the LCL. And then the storm environment we just based on a mobile mesonet from STEPS. So some of the results. This is one of the ways we visualize it, and it's kind of a lot, so I'll step through it just with this one panel. On the y-axis, we have the diameter of the hailstone, and then the height is the y-axis. Each of these columns, or each of these little rows, is a different hail size that we initialize. And then the colors are time since the model initialized. So basically, every one of these curves is showing, with time, how is the height and the size of the hail changing. And then, like this kink down here is when it falls below the melting, or the LCL, so it's subsaturated. So we have all 6 parameterization combinations. I'm going to start by looking at the melting parameterizations. So we're just going to look at the bottom slot. It's easiest to see with the bottom. We'll start by the behavior of how the model behaves is different a little bit based on if you're looking at somewhat bigger hail or smaller hail. I will give the caveat, all this hail is relatively small. All this hail, we all simulated hail less than 40 millimeters, so it's not very large. Some of the results are going to be, would be slightly different if you get larger hail. So caveat with our results, they're small. But for the smallest hail, less than 10 meters per second, or 10 millimeters, if we start with Wang and Chu 2020, you see the curve starts pretty vertical, and then it curves somewhat sharply. This suggests that the hail initially, when it starts to fall, it's melting really slowly, and over time that rate increases. The Zhang and List, you get a similar picture. You see straight, and then this curve is even sharper. So this Zhang and List melts even faster at smaller sizes. And I'll show later on that's actually an issue with this parameterization. And then finally, Rasmussen and Heimsfield, this curve is a little more consistent. You don't see like a sharp curve as much. It's more smoothly curved throughout, suggesting that there's more of a constant rate in this parameterization. So what we're seeing, all these behave differently, and this is also true for the larger hail. For Zhang and List, this larger hail, larger than 20, you see this line is almost straight, suggesting that the hail basically just falls straight to the surface. Hardly any melting occurs. On the other hand, Rasmussen and Heimsfield 87, there's more of a slope, suggesting you do get some melting at least in the sizes. So each parameterization behaves a little bit differently, which is interesting. And then you get quite a bit different when you start looking at the terminal velocity. So on the top here is the empirical Heimsfield et al. 2018. And then this is the Rasmussen and Heimsfield 1987. And what I want to draw your attention to especially, you can see it best over, again, at the small sizes. You see these bright orangish reddish colors here, and they're absent here. This is telling us that the Heimsfield et al. 2018, the hail is falling much slower. And so that's the defining characteristic of this model. I will say, Becky, also AER, has done some work with larger hail, and she sees kind of the opposite, that Heimsfield 2018 actually caused bigger hail to fall fast, but at this size range, it makes it fall decisively slower. So when we put it all together, we found that the behavior of falling hail is really sensitive to the parameterization, and a lot stronger than we were expecting. This was actually supposed to be just like a little starter project for me as I got used to running the model, and then I was like, oh, this is actually more than we thought. So that was interesting to find. And it also started to bring up the question of like, how do we, so we see these variability, how can we give an idea of like, is this variability a big deal? Is this normal variability, or is this like excessively large? So for this point, what we did is then we wanted to see, okay, how does this parameterization variability compare to like environmental variability? So we did additional simulations where we either increased the temperature or decreased the moisture in the environment and reran it. So, and the changes we did in the environment were based on climatology in Kansas in like June. So they're within range. We increased temperature by up to 3% Kelvin and reduced the mixing ratio by up to 30%. And so the way that I'm going to show this is these heat maps. So these are 2 different sizes. In each panel, you have the different parameterization options here on the bottom, and then these are the different environments. This black square is what we call our reference state. So it's the original environment, and it's Rasmussen and Heimsfield 87 terminal velocity and melting parameterization, which is most commonly used. And then what's most important, and what you really only need to focus on is the different colors. So the colors are telling you how different is each one of these simulations from this reference state. So if it's red, it's showing that it's bigger than what happened in this reference case, blue, smaller. And this is diameter, forgot to mention that. We also did similar plots for the height of the hail, so what was the final height, whether it hit the surface, melted completely at what height it happened, or if it was swept upwards, and then how long it took the hail to fall as well at the bottom. So I'll start by looking at these big hailstones. This panel right here is height, and you see everything's gray, everything hits the surface. So all the hail in these simulations start at 20 millimeters, hits the surface. However, you notice that there's quite a bit of variability in the diameter of the hail. And I forgot to mention, if you look horizontally across these heat maps, you can get a sense of the variability across the different parameterizations. And then vertically is the environmental variability. So you can see here, you see a lot more color variability as you look horizontally than vertically, suggesting that the variability across the parameterizations is larger than the environment. And this is also true for how long it takes to fall. This very striping is basically each one of these every other column is the Heimsfield 2018 empirical relationship that makes it fall so much slower. So that's why you're seeing those stripes. But in general, you're seeing that the variability is greater across the parameterizations than the environment. For the smaller hail, you see that there is now differences in the height. So some hail melts, some hail reaches the surface. You can see that here. There's a bunch of zeros here, so a bunch of this hail melts, but some of it makes it to the surface at rather large sizes. So you see variability again across the parameterizations, especially again in terms of how long it takes for the hail to fall and the height. And again, this variability tends to be greater horizontally than vertically, so we're seeing there's more variability across the parameterizations than across the environments. So basically, this variability is often as large and even sometimes larger than the environmental variability. And this variability is not limited to diameter. A lot of times when you see hail studies, they're really only focused on the diameter of the hail. But issues such as what height does the hail completely melt, or how long it takes to fall, can have implications for like the storm structure or just warning issues. So just to briefly say, at this point, what we did, which is what we just published, we created this simplified hail trajectory model that we call HailCast. It's Python-based, and it only considers melting hail. Some of the advantage of it is that it has multiple parameterizations that you can test at the same time. It's also very efficient. I can run thousands of these simulations just on this laptop in a couple hours. That's a really nice feature of it. We have found that the simulated hail is really impacted by which parameterization you choose. And it's not just the hail size, and that this is often larger than like the standard environmental variability. So it does bring into kind of important implications for what's the, when you're simulating hail, what does this mean about where your hail is, what kind of impacts you're going to have. So what we kept getting through a lot of this work, and we still get, is okay, we've seen so many parameterization variability here, so much of it. Can we say one is more realistic than the other? Can we eliminate some? How do we do that? So that's been our focus now for the last couple of months and moving forward. So yes, I'm going to start going into like this evaluation work. As I mentioned, I'm going to talk about 3 kind of projects we have going on. Each one's going to be a little more preliminary. So get to see some of the new stuff and some hints of what we're going to do in the future too, including stuff with ICECHIP. So the first thing that we did is we have, for our work with NASA, we had access to a database called the Ground Validation System Validation Network Multi-Platform Precipitation Feature. It's a mouthful, VNMPF, which is not necessarily easier to say. But basically what they did is they combined, they took the GPM satellite and they identified storms when the GPM passed over a storm that was being detected by a NEXRAD radar. So you have both the GPM data and the NEXRAD radar. This data set is available for about 9 years. A couple of advantages is that the GPM satellite has radar on it, and it includes a hail flag when they think hail is present. There's caveats with that. We have some work trying to work on that, but we have some sense of which storms might have hail in it. And then there's also, there's a study that showed you could use, or developed relationships that you could use reflectivity from the -20 degrees sea level to estimate in-cloud hail size. Again, there's a lot of caveats with that. And because of the small wavelength of the GPM satellite, we're not going to be able to estimate any big sizes of hail. All this hail is small. But at least we have some estimates of in-cloud size, which is hard to get. So with those things, with hail flag, we have identified about 2,000 storms. They're shown here on this map. They're clustered around the NEXRAD radars as expected. And then this is showing the distribution of hail sizes from those 2,000 cases based on 6 different relationships of reflectivity to hail size. And all these most of them are less than 20 millimeters. Some get up to like 35. But what we did is, as I mentioned, the great thing about hail melt is that it's efficient. So I can run all 2,000 of these cases in a couple hours on my laptop. So we did this the same parameterization combinations. This time we're using environmental conditions from a RAP reanalysis data near the location of the storm. For simplicity, we're assuming there's no vertical velocity. And then, again, hail sizes from that reflectivity relationship. And at this point, it was given this large size of data we now had, we could start looking at statistical relationships and kind of identifying how the different parameterizations respond to different environments. So one of the first things we did is we wanted to see, okay, how much melting do we get based on the initial size of the hailstone and the melting level height? So what these are showing, all these, is on the bottom is the initial size of the hail. On the y-axis is the initial height. And then the colors is how much hail melt occurs, or how much of the hail melts. They're all different color bars, which is okay. We don't need to worry about that. It's mainly just the colors, with like the whitish, pinkish colors being the greatest. So these two, Rasmussen Hinesfield 87 and Wing and Chu 2020, both of them have a very similar relationship where you get the most amount of melting at your largest hail size that start at the highest altitude, which makes sense. You would expect these have the longest way to fall and the most mass to melt, so you would expect they would melt the most. Zhang and List is very different. They get their peak melting here at this like moderate size, which we were very confused with. So what we did is we decided to isolate some cases just in this region where we had moderate sizes in our case and then high melting levels. And so this is showing a time series of a bunch of those plots. So on this, the y-axis is each time step, the diameter is on the y, and then the color is how much melt occurs at each time step of the model. And so this is the Rasmussen and Hinesfield 1987. And this one is kind of what you expect. You start over here where the model just starts. And so you have, you're near the freezing level, you don't get a lot of melt. Then there's a sweet spot where you have relatively large hail and you have warm conditions, so you get a lot of melt. And then as you get closer to the surface, your stone gets smaller and smaller, and you get less melt. So that makes sense. Zang and Liss, you get that slow melt at the beginning, but it just kind of continually increases. And then you have this weird behavior down here where, like at the last time step, you get a ton of melt, like the size just becomes very small, and you get the most amount of melt at that time step. So we started actually looking at the parameterizations, and all these parameterizations have the same basic form of like A over B times C. And Zang and Liss is the only one that has a diameter term in this B in the denominator term. So it's actually causing that as your hail gets smaller, you're actually getting more melt until it eventually becomes unstable, and you just get this giant amount of melt right at the end. So we aren't considering Zang and Liss. The next slides that I'll show you, we don't have it in there anymore. We actually have a different one now we use, but the interesting things you find. The other thing we're using this data set for is we're trying to pair it with CoCoRaHS. So this is the Community Collaborative Rain, Hail, and Snow Network. We're teamed up with people from CSU and University of Alabama, Huntsville. And they've been, CoCoRaHS comes out of CSU, and it's a nationwide volunteer network that report precipitation. They're best known for like snow and rain, but they also do hail reports, and that's what we're using. So what we do is we take all 2,000 of our cases, and we try to find which cases are co-located with the CoCoRaHS report that includes a small hail size estimate and a large hail size estimate. And because it's kind of a strict criteria, we do put a large bound. We say that the hail report has to be within 1 hour of the storm and within 100 kilometers. And with that, we end up getting 60 storms out of our 2,000. So it's quite a bit smaller. Those 60 storms are shown in red on this figure, or I'm sorry, in green in this figure. Red is a different aspect. And then this here is showing the distribution of the surface sizes that are reported. Most of them are smaller than an inch. We do have a couple greater than an inch and up to 2 inches. So what we did is we're now simulating these 60 cases. We've changed it so the environmental conditions are from ERA 5. We're also testing an ensemble of vertical velocities ranging from 3 to -3 meters per second. And we have a few additional melting and terminal velocity parameterizations since we have less cases now. And in general, we say one of these hail melt simulations is validated if the final hail at the surface actually reaches the surface and it's within that small to large size range reported by CoCoRaHS. So this is we're still working on this. This is pretty preliminary, but we're showing a heat map here of the percentage of simulations that verify out of these 60 or so, 60 or so, but we have, the numbers are higher because we have a bunch of ensembles here. On the left, or on the y-axis, is our different melting parameterizations. The x-axis is terminal velocity. In the melting parameterizations, the two we've been talking about are right here. The Wang and Chu 2020, that's actually pretty clearly been one of the ones that hasn't been performing as well. Rasmussen Heimsfield is performing quite well, and this Goyer 1969 performs similarly. So, but it's good to see that Rasmussen and Heimsfield is ranked so high, so that is one of the most common ones used in the broader community. The thing that really surprised us is, so in the terminal velocities, this column right here, this is the Heimsfield 2018, the empirically derived one, and that one is by far outperforming all the other parameterizations. The other terminal velocity parameterizations, they're all based on some variation of that best number, Reynolds number relationship situation. So we were really surprised because it does cause the hail to fall so much slower. So that's one aspect that we'll talk a little about ICECHIP, and that's one aspect of ICECHIP I think could help us really see is this is actually something. But this project is ongoing. The CoCoRaHS is trying to work on increasing citizen science participation, especially in the southeast, so we can hopefully get some more insight into what's going on with all the melting in the southeast. And then finally, what we did this summer is ICECHIP. So ICECHIP is the In-situ Collaborative Experiment for the collection of hail in the plains. This occurred in May or June of this year. There's a large number of collaborators working on this, range from academia to private industry, as well as international. We had people, groups from Canada, Germany, and Australia come out for it as well. We were in the field for 46 days. We were very lucky. That was very active. We had 5 true rest days. A total of, we deployed 24 different storms, and 18 of those we were able to collect hail associated with them. We drove over 15,000 miles, all the way from South Texas to North Dakota and Billings, Montana. A total of over 7,000 hailstones were measured in the field, and then a large subset of those were crushed to do some testing. And then we also have 18 boxes of hail that we sent back to Boulder that is now being studied by Anthony, who used to be here. So what was ICECHIP? We had 5 main goals. One was to better understand how hail develops in these storms, including their in-storm characteristics and how they fall. There's looking at how the hail moved through the storm and how that relates to the updraft. We also want to look at some environmental features and geographic location and how that relates to how the process is acting on the hail and its predictability. And these last 2 are related to hail surface properties. So we had a couple insurance company out with us, and so they were really interested in looking at hailstone properties and how that impacts their damage potential. And then also groups looking at using radar and trying to see what is the hail relationship between the hail surface properties and the radar observations we have. So this is all this data is just starting to come online. So it's going to run through some of all the measurements we had to answer these questions if you're interested in potentially looking at it. First, we had a suite of near, pre-storm, and post-storm environmental observations. These were pods, mobile mesonets, and mobile sounding units. We had 4 radars. They were C and X band. They were mobile. And then we had isotopic characterization of the inflow. This is actually what Anthony was in charge of and what he did a great job working on. We had these really cool instruments that came out of Germany and Australia. They're called hailstones. So these are little instrumented little balls or cubes that they released in balloons into the updraft or the inflow and got ingested into the updraft. So you can get like information about how hail is freezing, would be freezing on a hailstone like this, and also updraft information. Hail pads. We had hundreds of them. These are essentially just squares of styrofoam that we put out on the ground, and then they get dented, as you can see with the hail when you get a good storm, and then we can take high resolution pictures of that, and that can tell us information about the hail size and things like that. We had a series of astronomers. This one on the left is actually an impact astronomer, so they could tell us how strong it is, the hail hits the surface, and then we had more traditional visual PIPs astronomers. A large aspect was hail collection, so after every storm we'd spend several hours in the field afterwards collecting hail. It was measured, weighed, 3D scanned, and then it was also crushed. And a subset of them were then sent also back to NCAR. Also in the post environment, University of Colorado had their UAS team out there where they would take hail swath video to try to get swath measurements. And then I was involved with deploying 2 instruments. First are these high-speed hail cameras. That these were actually developed by the University of North Dakota. They started using these for looking at ice crystals, but they retrofitted them a little bit, added a little bit extra padding on the top, and deployed them in hail. And then also a more experimental instrument called a super mobile hail observatory. Basically, we had a funnel, and we would deploy this ahead of the hailstorm. So the hail would fall through the funnel into this box that had a cooler in it. So it would try to collect the hail and freeze it, hopefully, before it melts significantly. There's some issues with the hail freezing together, but it would get frozen really quickly. We had an anemometer, a hail pad with a camera on top, so we could look, get a better more understanding of how hail pads respond to hail. And then we had this box here that was a vertically pointing radar, so we're hoping to get terminal velocity measurements from the hail themselves. So there's a lot of observations, and a lot of them are starting to come online now. What we're going to do for us specifically in terms of hail melt, our simulations, there's a lot of unique validation opportunities in general, whether it's for hail melt or other studies. Many of these cases are going to be some of the most comprehensive documentation we have of surface hail size distributions there are. So that's going to be really exciting. I'm also excited about some of these terminal velocity results. So these are some quick look images from the high-speed cameras. So this is actually a hailstone that you can see droplet shedding. And then this is, we think it's about a 3-inch hailstone and estimated to be falling 60 meters per second. So it's pretty crazy. Oh yes, and this is Anthony enjoying all his boxes of hail. This is all his hail at NCAR he has. So he's been busy doing that. And then hail melt is also, we want to update some physics. We want to include non-spherical hail, some new droplet shedding, and also whatever new parameterizations come out of here. And I'm personally interested also in getting some radar involved, so I can connect a radar emulator to hail melt, and so we can start trying to look at how does understand how radar emulators simulate hail and how that compares to observations. So in general, ICECHIP operations are done, but it's just kind of getting started. And so a lot of things to do. These are 2 websites if you're interested in looking at the data in any way. There's a lot of options to look and see. And it's not just hail. I like to say we actually were really lucky. So the big derecho that went through this spring, we were actually on a storm just at the very beginning of that derecho in far western North Dakota. So there's other, as I say, there's hail, and then there's also a bunch of other cool stuff in the data set you can look at. So what we've done is hail melt and terminal velocity are important processes that impact the damage potential of hail. There's been a lot of work developing parameterizations, describing these processes since the 1960s, but there hasn't been a lot of comprehensive analysis that compares these two, especially in a robust way. So that's what we did. We've developed this Python model that allows you to very effectively and quickly simulate these falling hail in different environments. And we include different parameterizations, and there's a lot of parameterization variability, much more than we expected. So what we're doing now is we're trying to understand which parameterizations are more accurate, and then also, potentially improving parameterizations in the future. We're using citizen science, CoCoRaHS, to try to get some help us validate the size, and then ICECHIP is the big thing for our future, validating hail size, terminal velocity, but also just all the data that's there. So yeah, and I just kind of like this picture that it's, yes, we found hail and cactus at the same time when you chase in Texas. So thank you.
We have plenty of time for questions, so let's start with the students. What would you like to ask Hannah? Okay, Noah.
Thank you. Great talk. I have a question for you. So I don't know what slide it would have been, but it was like panel D for the larger hailstone simulation. Do you know what's going on with that, where like they're literally all melting?
Is it this one or the other one?
That one, yeah.
So like here?
Yeah.
Yeah, so basically once, so that it's actually the height. So this is the height, so it's all reaching, they're all hitting the surface. So basically at this point, this is a little bit lower than I expected, but especially once you get to about an inch in all our simulations, the hail just falls straight to the surface and doesn't, it falls so fast it doesn't have time to melt. So everything is hitting the surface in this case. Yeah, so it's one, it's, our results suggest that like for hail melt, it's more significant if you have smaller hail. But again, how that fits in, we saw potentially there's a lot of melt in the southeast U.S. where they have big hail aloft. So still something to find out. But in the models, they're saying once you get close to an inch, it just falls without melting very much.
So I misunderstood it, and it actually was completely unaltered through all of those.
It doesn't unalter, so there is melting, some melting going on. This is the diameter size here. So this is, you do see there's color shading, so there is some difference in the diameter. But it is all reaching the surface.
Okay.
Yeah.
Tyler, Lillian?
If a parameterization ended up missing so badly, why did it get published and used, generally speaking?
Yeah, so it's a lot of times that's a good question. There is a challenge, some of these parameterizations were developed based on modeling results only. So there's that. And so they might not have had as close analysis. Also, a lot of these, one of the drawbacks of some of these are developed in laboratory settings. So you can't, how many hailstones you can test in a wind tunnel is limited, and you're limited by the geometry of the wind tunnel and things like that. So a lot of it is kind of limitations of testing. And yeah, it's kind of whether you can test a lot of environments and different sizes. Yeah.
When you do the simulations of the different parameterizations for hail, how much of a factor or non-factor is the response of the melting hail to the environment and then the feedback that would have? I would assume if you're melting, there's a phase shift involved, the environment is getting perturbed. That might have implications for the updraft or the downdraft, depending on the environment, and that would have feedbacks into the velocity as well as the melt rate.
Yeah, that's a really good question. And for us, we don't see those because we are fixing our environment. But yeah, when you do like the full hail cast, which this is from that is run in WRF, you can get those simulations. And so yes, we would, if we were running this with an interactive background, yes, we would expect to see there would be some potential impact. I think it's hard to say a little bit of like, how much, if you're having evaporative cooling, how much of that is and whether that will impact it significantly. But yeah, it would definitely, we are aware, we just don't include that.
Thanks. Yeah, why is there the anomaly of South Carolina as far as extent of hail damage, even though it's so far from these belted states that are once heavily hit by it?
I do not know. I'm assuming they had some good hailstorm there last year. Really, one hailstorm can greatly impact this. Texas in particular, I'm pretty sure the reason why it is listed as $1 billion is because back when the government was still doing the $1 billion events every year, there was a $1 billion hail event in Texas last year. So it's really, if you get a really big event, it can definitely skew your statistics in some sense. So I'm assuming that's probably what it is, but I haven't looked exactly yet. I don't know why South Carolina necessarily sticks out, but
Just also an observation, I forgot about this. I was at the Louis Tomlinson concert. It was warned.
Okay.
At the time, it had been postponed multiple times, or delayed. And there was hail that was flung, I think, out the top of the updraft ahead of it.
Oh.
And me and my group, we were able to get to our car right before the hail started because
That's
they
good.
weren't paying attention to it. But it was like a piece of gravel hit the ground.
Oh.
And then later another piece of gravel hit the ground. And it was hail. And another piece of hail hit the ground. And then it started like pouring.
Wow.
After that. So it was really interesting.
Yeah. Yeah, and that amphitheater is not good for those situations. You are very isolated. You're on the side of a mountain.
All right, more questions from the room? Yeah.
So on these melting parameterizations, I guess, like how in detail do they get? Do you get like boundary layers around the side of the falling and look at like heat flux out of that, or what's the?
There is some, so yeah, there is some like old papers that they have the diagram of like rotation inside the hailstone and the moisture. So yeah, there is like they are thinking of hail heat conduction and stuff across there. I'm not sure exactly how precise these are, but there has been at least laboratory studies that show like there is how they get a torus also of water on the outside of the hailstone as it melts. I don't think these parameterizations necessarily like model or represent that, but there's at least awareness of that. I'm not sure it's actually represented in these parameterizations.
I can imagine that, like, I can imagine that, if you've got a suspended hailstone in a wind tunnel, you can get all sorts of geometries and structures that would exist that don't exist once you start allowing the hailstone to collide and other stuff.
Yeah, and wind tunnels in particular, they don't allow tumbling at all. Like they're usually tethered. Granted, whether hailstones tumble is a surprisingly controversial issue, but.
Why is that?
There's some thought, like, some people think, like, because usually if they're, like, oblong, they'll fall like this, so whether it's how unstable is it, or if it just spins, or whether it actually is, like, tumbling everywhere.
As an avid gardener, does your knowledge and experience with hail affect your gardening?
We've been lucky it hasn't. We came close. I'm in Fort Atkinson, so there was the big hail. We didn't have anything in our garden yet, but we were, a couple of miles away from some 2-inch hail. But we've been lucky. We haven't done it yet. But I'm like, do we need hail covered?
Right?
I have thinking about the surface texture and how you might want to think about that in like a parameterization in the future.
Mhm.
I'm wondering about like hail with spikes versus hail without spikes and how that impacts like all of these things.
Yeah.
Diameter, melt, fall speed. Like, I don't really know that much about it. So I'm
Yeah,
wondering if you
there's definitely some people looking in, there's some parameterizations, but yeah, it gets really complicated based on like where the spikes come and if you get like collection of water or heat in those little crevices, it gets really complicated and also a lot of like, we don't know. But yeah, there's definitely people like looking into that and like it's, some of these parameterizations were, you did allow lobes, but yeah, and then you even get to like surface roughness even, like the texture, so.
I know you had a question.
Yeah, so this is sort of like, I'm just thinking about that State Farm hail damage in
Mhm.
there. Do you think Wisconsin made the cut with all that crazy hail, or like, was it pretty like small scale in terms of like the actual?
From this year, I don't know. Hard to imagine. I mean, we had a big event, so it could have. I mean, you said there was a lot of damage. So yeah, we'll definitely have more damage than we did last year this year. But yeah, I'm not sure it necessarily hit the $100 million mark, but we'll see.
So, sorry.
Yeah.
It's really interesting talk. It was really, really fun to see all the different ways you're measuring this, and especially this last ICECHIP's campaign.
Mhm.
So it seems to me that like the ideal would be able to have initial conditions and measured initial conditions, and you're only getting the measured final conditions.
Yeah.
With ICECHIPs, are you gonna be able to back out, I mean, and with radar data, are you able to get initial size distributions at all to compare with?
We're gonna hopefully maybe try to. We're not gonna be able to get a ton. We're hoping that at least maybe we can see, like, is it, get a better idea of spherical, non-spherical, things like that. But yeah, it's gonna be rudimentary. We can't, there's a lot of like that mesh algorithm with radar. They try to do a lot with that. So yeah, we won't be able to do great with it, but hopefully a little bit of something. Otherwise we might do, which we tried a little bit with the CoCoRaHS data, is we just initialize a distribution and see at the surface, like, okay, what size reaches the surface, and then we can back out, like say, okay, maybe the hail was this big a loft. Like if we had a 1 inch hail, okay, 1 inch hail corresponds to 1.25 inches in our simulation of loft. That's another way we can try to do it. But yeah, we have one data set that has one part, one data set has the other, but yeah, the in-cloud hail estimate's gonna be hard. We'll see.
You need to maybe resurrect the armored P3 and convert that into self-driving.
Yeah, the one aspect that we'll be able to do a little bit is the high-speed cameras, that we will be able to have some direct measurements that way. Granted, that's only like a foot off the ground, but still, it's something.
Yeah, thanks. So did I understand you say that the plan is to scrap all further use of aircraft for hail research?
Yeah, they're not going to be able to do that. We had planned originally, like, there's different aspects you could do hail research with an aircraft, just like inflow kind of things. But yeah, pilots will not fly into a storm anymore. They're very much against that, rightfully so. I don't want them to fly through these storms. The best we can do is, yeah, like we had the UASs, UAVs that tried to go right after the storm to look at the size distribution at the surface, but even those, they're not going to fly them in a storm. So.
Do you get drops on that at all, or is that just too?
Yeah, you would still need the plane in the storm though.
To
Which
measure
would be-
the actual.
Yeah, to get like the drops on in the storm. Yeah.
Oh yeah, by the way, just, it's
I have a question, Hannah. You spent a lot of time with hailstones this spring in the field. Was there anything particular that was surprising, just being out there and actually seeing so many hailstones while you were out there?
Yeah, I think one of the biggest things we were surprised, sometimes there's a bunch of little, moderate-sized hailstones, and then there'd be a random 3-inch hailstone amongst all the other ones. Like no other, just one random 3-inch hailstone. And you're like, okay, what happened here? And so I think that was interesting. And then yeah, there's some really strange looking hailstones out there. That was always kind of fun to see. But yeah, the random giant ones were interesting.
All right, well, let's thank Hannah again.